this video I'll be covering problem 76. Problem 76 says, a uniform beam is suspended horizontally by two identical vertical springs that are attached between the ceiling and each end of the beam. The beam has mass 225 kilograms and a 175 kilogram sack sits on the middle of it. The beam is oscillating in simple harmonic motion with an amplitude of 40 centimeters and a frequency of 0.6 cycles per second. A. The sack falls off the beam when the beam has its maximum upward displacement. What are the frequency and amplitude of the subsequent simple harmonic motion of the beam? So for part A, we want to find what the spring constant is. So we know that the frequency is 0.6. And so we use the frequency equation of omega over 2 pi, which is same thing as root k over m over 2 pi. So we know 0.6 equals that. So we multiply by 2 pi on each side. And we'll have 3.77 equals square root of k over m. And then we'll square both sides. And we'll have 14.22 equals k over m. And we know what the mass is. So we use the mass before the sack fell off, so we can know the spring constant, because the constant will never change no matter the mass. So then for the mass we plug in 400, which is the 225 kilogram beam plus the 175 kilogram sack. So then we multiply by 400 on both sides, and we'll get 5688 newtons per meter equals the spring constant. And mass 2 is 225 kilograms, which is just the mass after the sack fell off, because it's just the beam. So then we just use a frequency equation again. Frequency equals root k over m over 2 pi to find the frequency. And so we plug in k and this mass into here. So we'll have root 5688 over 225 all over 2 pi. And we'll end up getting 0.8 hertz for the frequency. And then we want to find the amplitude. So we want to find what x is. So we know that force equals kx. And so we divide by k, so we can get x. So we'll have force over k equals x. And so then we make that mg over k equals x. And we just plug in the values we know. So we know g is 9.8, we know k is 5688 newtons per meter, and we know the mass is 400. So we want to use the mass before the sack fell off again. So we do 400 times 9.8 over k, which is 5688, and we'll get 0.69 meters for this. So then we want to subtract the the amplitude that it told us it had originally, which is 40 centimeters, which equals 0.4 meters. And we'll have 0.29 meters for the oscillation. So then what we do, we use that to subtract it from the new x for the new mass. So we do this again, we have mg over k equals x, and instead we plug in 225 again. So I have 225 times 9.8 over 5688, and that will equal 0.39 meters. So this 0.29 meters is just the resting length of the spring, the resting distance that's stretched out. So then we'll subtract this. We'll subtract 0.29 meters from 0.39 meters again, and get 0.1 meters for the new amplitude for part A. So these are the frequency and the amplitude for part A. And now we go on to part B, and we'll want to keep this spring constant in mind, so I'll leave that there. Alright, so part B says, if the sack instead falls off when the beam has its maximum speed, repeat part A. So now we want to find the maximum speed. So we know that V max equals the amplitude times omega. And we know that omega equals root k over m. So V max equals the amplitude times root k over m. And so we just plug in the values we know from before the sack fell off. So the amplitude is 0.4 meters before it fell off. The spring constant is 5688, and the mass is 400. And when you work all this out in your calculator, you'll get that the maximum speed before the spring fell off was before the sack fell off was 1.51 meters per second. So then we don't need to worry about frequency, because frequency is just root k over m over 2 pi, and after the sack falls off, the mass is the same, the spring constant is the same. So we'll just end up getting the same answer as last time. Let's get 0.8 hertz again. But for the amplitude, we will get a different answer. So we want to do conservation of So actually, forget about this first part. We just want to do conservation of energy to find the amplitude. So what we do is 1/2 Ka squared equals 1/2 Kx squared plus 1/2 mv squared. So we can take out the 1/2s, and then we'll have Ka squared equals Kx squared plus mv squared. Oh, just kidding. We do want to remember this first part. So Vmax was 1.51 meters per second. And so we plug in the K's. We plug in K, which is 5688 to here. We plug in X, which is just the resting distance of the spring, which is 0.29 meters. And we plug in the mass after it falls out, so 225 kilograms, and we plug in the Vmax, which is 1.51 meters per second. So we'll have 5600 or 5688 times a squared equals 5688 times 0.29 squared plus 225 times 1.51 squared. So what you'll end up getting is 5688 a squared equals 991.38, and you just divide by 5688 to find a squared. So we have a squared equals 0.174. Do the square root of that, and then you get amplitude equals 0.42 meters. And that is problem 76.